Hello, Chem 213 students, and welcome to the first lecture for our last chapter in Chem 213. This is going to be on the biomolecules lipids. Now, an interesting thing about this class of biomolecules is unlike the previous biomolecules that we've talked about, amino acids and proteins, which contain the functional groups amine and carboxylic acids and are defined by those functional groups. And unlike carbohydrates, which are defined by their polyhydroxy aldehyde or polyhydroxy ketone functional groups, instead, lipids are a broader class of molecules that may have a variety of functional groups, but are largely classified based on their lack of solubility in water. And so we all know the old adage, oil and water do not mix, right? And so we have here olive oil. Olive oil doesn't mix with water because it's not very polar. And so what we see here instead is we see oil usually floating on top of water. It's usually less dense than water. But there are a lot of other lipids other than like dietary oils. There are lots of important lipids in our body that are important for the function and the structure of cells, for example. So let's get started talking about lipids. While we're talking about lipids, we're going to talk about hydrogenation of double bonds, specifically fat molecules. And so if you forgot about the addition of hydrogen, H2 and platinum or whatever, or H2 and nickel as it's industrially done, then you'll want to review that. You want to review the part about radical autooxidation and antioxidants. We're going to talk about the oxidation of the carbon that's the vinylic carbon for alkenes, double bonds, carbon-carbon double bonds. And finally, the hydrolysis of esters in base. This is referred to as saponification, and as the name implies, this is the way soap is made from fats. Including your skin. So if you get base on your skin in lab, it turns the oils in your skin into soap, and then those wash away, and that's not good for your skin. That's how you get burns from bases. So lipids are naturally occurring compounds that are soluble in nonpolar solvents, such as hexane, let's say, or something like that. They're not soluble in water. That's the key idea there. They're divided into two large classes, complex lipids and simple lipids. And unlike the names might imply, simple lipids can be quite complex molecules, and complex lipids can be small molecules. What differentiates one from another is that complex lipids have esters that you can hydrolyze in them. And so that means so these contain esters. And you can hydrolyze these and break the lipid into smaller fragments. Simple lipids do not have esters, so they cannot undergo the hydrolysis of esters. So that's the difference between them, not the size or the complexity of the molecule, but actually whether they have an ester functional group or not. So lipids have subcategories that have structural similarities. So we have the two big categories, complex lipids, which can be hydrolyzed, and simple lipids, which cannot. Complex lipids include the classes waxes, triglycerides, or these are the dietary fats and the way fat is stored in our body, phospholipids, which are often parts of cell membranes, and then simple lipids, which include steroids like cholesterol and the sex hormones, prostaglandins, which are involved in pain responses and inflammation, and terpenes, which have a variety of functions. So waxes are those lipids that contain an ester functional group with two long hydrocarbon chains on each end. And so this makes them extremely water insoluble. An example here is spermaceti wax, which is a wax isolated from the heads of sperm whales. But there are lots of other examples of waxes, like the wax on the outside of an apple, for example, or a leaf. Plants make these as a protective coating. Triglycerides, so these are the dietary fats, and they also contain esters. They are a triester. Here with long chain fatty acids. Again, these long chain hydrocarbon parts here are the parts that make the molecule insoluble. So although these are polar functional groups here, the esters, the largest part of the molecule here is nonpolar. Finally, we have phospholipids. So phospholipids are like triglycerides, except for instead of one of the esters, we have a so-called phosphoester. And then there'll be another group attached to it. This happens to be choline, as it's called. Overall, this phospholipid is called a lecithin because it's a phospholipid that has choline attached to the phosphate group. So a few examples of simple lipids would be cholesterol here. Notice that the cholesterol does not contain an ester functional group. Prostaglandins, which again are involved in the pain and inflammation response, and limonene here, which is a terpene characterized by these units that join together in polymerization reactions and have double bonds in them, carbon-carbon double bonds. So let's start by talking about waxes in detail here. Waxes are esters that have a high molar mass, meaning they got a big old hydrocarbon part on each side of the ester functional groups. If you hydrolyze the ester, you get an alcohol from the side of the ester here that contains the oxygen atom here, and you get a carboxylic acid from the other side. So if we were to hydrolyze this, we'd get a carboxylic acid with 16 carbon atoms, and we'd get an alcohol with 30 carbon atoms. And this is called triacontyl hexadecanoate. And so this is beeswax is primarily this wax right here. So waxes can differ in the length of the carbon chains, and depending on where they're coming from, they will have a different number of carbon chains on each side of the ester, and they serve a variety of functions in living systems. These, as I said, include like protective barriers for plants on their leaves or on the fruits. These include many other functions, but often they are on animals, for example, like birds, they'll often have a waxy layer on their feathers, and that's what makes the water bead up and roll off. So there's a variety of functions of waxes. They generally involve protecting the organism from water, because water, it does not mix with this very nonpolar waxy molecule. Triglycerides are the dietary fats, so they're the way that our fats are stored in our bodies when we eat animals or plants that have fats or oils. These are the package that they come in. They are triesters, so triglycerides are formed from 3 ester groups, all attached here to a series of 3 carbons. The molecule here, and these can be hydrolyzed again, and you get alcohol on one side. On the oxygen side, you get an alcohol group, and on the other side, you get a carboxylic acid group when they're hydrolyzed. So here is the hydrolyzed form. So the alcohol groups here, we have 3 alcohol groups from the 3 esters. This molecule is called glycerol or glycerin, and this is an important biological molecule. In fact, your body can metabolize glycerin for energy as well. It metabolizes it in a different way than the fatty acids. But the fatty acids are what our body uses for energy itself primarily. And they're called fatty acids, as you can tell, because they have a carboxylic acid group. And then they have a long non-polar hydrocarbon chain, which is the fatty part. So fatty, the hydrocarbon chain, acid, the carboxylic acid. So if you ever wondered why they're called fatty acids, that's why. They have a carboxylic acid functional group. And then glycerol or glycerin is kind of the unit that joins them together when they form the triglycerides. So triglycerides are used for storing energy in organisms, and they are an efficient way of storing energy because when these fatty acids are metabolized, or these triglycerides are metabolized, they can produce 9 calories. We say kilocalories. That's a kilocalorie is a dietary calorie, 1,000 calories. Which, remember, a calorie is the amount of energy needed to raise the temperature of water by 1 gram of water by 1 degree Celsius. Fatty acids, basically, for the same mass, will store twice as much energy as carbohydrates or proteins, which only metabolize to 4 calories of 4 dietary calories per gram. So, if you're carrying around energy to store for later, Your body would prefer to be efficient and store it as fat because you can get twice the amount of energy out of metabolizing the fats per gram versus the carbohydrates and proteins. That is not to say that your body doesn't have some stored up carbohydrates. It has usually more or less 3,000 calories of carbohydrates stored up in the form of glycogen, which is a polysaccharide. However, for anything greater than that, and those are stored in your muscles for direct usage when needed. However, for longer term usage, additional energy is stored as fat and then is used as needed. So fatty acids can vary in length of their carbon chain. They generally range from 12 to 20 carbons in length, and they can be saturated or unsaturated. And so when you hear of saturated or unsaturated fats, they're literally referring to whether they have a carbon-carbon double bond or not. Okay. The saturated fats do not contain a carbon-carbon double bond. So here's an example: stearic acid. It's saturated. There are no carbon-carbon double bonds in its hydrocarbon chain. In unsaturated fatty acids, there is a double bond, and that double bond is always in the cis conformation here, or Z, on the same side. I hope you remember Z, right? This is Z, or cis. You can label it either way. And this produces a kink or a bend here in the fatty acid, and the result is that they cannot stack as well as a unsaturated fatty acid. So you can imagine multiple molecules of the unsaturated fatty acid being able to stack on top of each other very easily and having a lot of surface area for interaction, whereas a unsaturated fatty acid, where there's a kink in the chain, they cannot as easily stack on top of one another. And so the result is that they don't have as much surface area contact, and they're going to have less London dispersion forces holding them together. And for that reason, fats that are high in unsaturated fatty acid tend to be liquid at room temperature. They tend to be oils. And fats, and these are often the primary fats in vegetables and in not in meat, essentially. And in meat, you can sometimes have a lot of saturated fats, and those tend to be the solid fats on the meat, the gristle or the chicken, when there's a kind of soft chunk of fat. Those are primarily triglycerides that contain saturated fatty acids. So the shape, as I said, the shape of the fatty acid impacts its melting point. Linear side chains, saturated fats pack more closely. They have a higher melting point. And this is very important due to their higher London dispersion forces. Now, I can guarantee you 100% I will ask you on the final about why saturated fats tend to be solids with higher melting points, and unsaturated fats tend to be liquid at room temperature with lower melting points. It is because of the London dispersion forces between the hydrocarbon chains. Remember, London dispersion force is the primary intermolecular force between nonpolar molecules. And although there's a polar part and there's some dipole-dipole forces or hydrogen bonding, to be specific, in these molecules, the hydrocarbon chain is so long that the London dispersion forces are very important in the physical properties of the molecule. So each of these fatty acids will have its own name. You do not need to memorize the name. If you need the name, I will give it, or the structure, I will give it to you. But they do each have their own name based on the number of carbons in the fatty acid chain. So for example, if a fatty acid has 14 carbons in its hydrocarbon chain, it will be called myristic acid. If 18 carbons, it will be called stearic acid, a very common saturated fat, stearic acid here. And you can see that having a larger hydrocarbon chain means greater London dispersion forces, so the melting point is higher when you have a larger hydrocarbon chain on the fatty acid. However, these melting points here for the saturated fats are much higher than that for a similar unsaturated fat. So here we have an unsaturated fat with a double bond. It's called palmitoleic acid. It has 16 carbons in it, right between the 14 and the 18. However, its London dispersion forces are far, far lesser because of this kink in the chain, which doesn't allow it to efficiently stack and have a lot of surface area with the neighboring molecules. And so the melting point is at 0 degrees Celsius. To freeze palmitoleic acid, you're going to have to get it to the same temperature that water freezes at. Now, saturated fatty acids, again, have a higher melting point than unsaturated fatty acids. Also, higher molecular weight fatty acids have a higher melting point. For the reasons I described, they have greater London dispersion forces if they have a larger hydrocarbon chain. And the same is true for triglycerides. Okay, now if you have a triglyceride, the thing is that each of these fatty acid chains might be different. In this case, we're talking about, though, a triglyceride with 3 stearic acid fatty acid chains called tristerin, or here we have 3 linoleic acid chains, so it's called triolene. But notice the difference in the melting points. For the triglyceride with all saturated fatty acids, its melting point is much higher than for the fatty acid with 3 unsaturated, or the triglyceride with 3 unsaturated fatty acids in it. You can see the kinks in the chains here, which melts at a much, much lower temperature. So the triglycerides that have unsaturated fatty acids and have a low melting point below room temperature, we call those oils when they're liquid at room temperature. If they have a lot of saturated fatty acids in the triglyceride and they have a higher melting point, higher than room temperature, we call those fats. But they're both triglycerides. They're just differentiated based on their melting point at room temperature, which depends heavily on whether and how many unsaturated fatty acids are in the triglyceride. So unsaturated triglycerides can undergo hydrogenation, and so if you've ever seen a carton of margarine, or I can't believe it's not butter or something, it's going to say that it has partially hydrogenated vegetable oils, okay? And so a vegetable oil may contain double bonds in it. Here we have a triglyceride with 3 unsaturated fatty acid chains, and if we use hydrogen and a catalyst, just the same way we saw in chapter 8, platinum, nickel, something like that, we can hydrogenate the double bonds and we can turn them all into saturated fats. And so this is how we can take vegetable oils that are liquid at room temperature, chemically hydrogenate them, and then we can turn them into saturated fats, and those are solid, and now we can spread it on our bread. So the saturated triglyceride is going to be formed from the complete hydrogenation. Sometimes the hydrogenation is partial. This is where the partially hydrogenated vegetable oils come from. The reason why they're not fully hydrogenated, because if you made a bunch of this molecule right here, it would actually be very solid, like the solid in animal fat. And if we want it spreadable, we don't want it fully saturated. We want it partially saturated so that some of these remain as double bonds, so that it was a kind of softer texture, not really, hard solid. So that's where this is talking about partially hydrogenated vegetable oils. Now, there is a problem with partially hydrogenated vegetable oils, and that is that when this chemical reaction occurs, it can lead to isomerization of the molecule. So as I mentioned previously, all natural fats have a cis configuration on their double bond, on the same side, a Z. However, if you heat these up high enough, it's possible that the double bond can break for a moment and then reform. After that, a rotation has occurred on the single bond, and then ultimately a trans double bond exists in the fatty acid. Now, all of our enzymes and the proteins that catalyze the reactions to metabolize fats are built to metabolize cis fatty acids and not trans. And so our body cannot efficiently metabolize these trans fatty acids, and they remain in the body. And they can be metabolized by ultimately, but in the meantime, you've got basically this junk in your body that your body does not know how to efficiently handle. And that is as might be expected, bad for our health. These artificial trans fats are in fact really bad for our health, and so they've been largely banned in foods in recent years because of this. Margarine, for example, again, is partially hydrogenated vegetable oil. The reaction is stopped once the desired consistency is achieved. Again, if you keep saturating them, you'll get a more and more solid fat, and really you want something that's kind of soft and spreadable for margarine. Now, we discussed in chapter 10 how unsaturated fatty acids and any unsaturated hydrocarbon here can undergo an oxidation to produce a hydroperoxide. And so this involves a reaction here at the vinyl carbon, which can be abstracted in a radical chain mechanism, and then oxygen can then attach and then get protonated and produce a so-called hydroperoxide. These hydroperoxides are extremely reactive, and when you eat something, you don't want it to be extremely reactive. You want it to be basically non-reactive except to what the enzymes in your body are built to catalyze. Because if you have random reactions going on in your body, those can mess up the structure and the functions of your important molecules like your DNA. So when you leave fats out for a long time, eventually they're going to get this kind of off scent. And the reason why they have this off scent is because a lot of times this double bond can break and you get shorter chain fatty acids that don't smell very good. But also this is a sign of the oxidation of the oils. And so a oil that smells off or rancid is going to have an increased amount of these hydroperoxides, which when you consume them can initiate radical reactions in your body. And you don't want these kinds of free radicals wreaking havoc in your cells. If they reach the DNA, they can, be cancer causing. So it's not a good idea to eat old oils that smell off. Fortunately, you don't have to guess. If it smells bad, you probably don't want to eat it anymore. And you'll notice that this is especially a problem for unsaturated fatty acids. It's not a problem for saturated fatty acids. So you can leave saturated fatty acids out all day. They're not going to react with anything. It's the olive oil. So you'll notice olive oil has a shelf life. Eventually, it smells off. It smells bad. Canola oil, these types of things. It's because they contain a high proportion of unsaturated fats. So how does this mechanism go? Well, it starts with the initiation is going to be a hydrogen abstraction from the fatty acid. So this will be the fatty acid, let's say. At the vinyl position, it's had a hydrogen atom abstracted. And now it will react with oxygen here. And so we'll essentially, using our little fishhook arrows, hopefully you remember how to do that, we get a bond here. And notice that oxygen is written as a diradical, which it often is in the radicals chapter, because this double bond is very weak, and really each oxygen kind of wants to hog one of its electrons in the double bond, since oxygen is super electronegative. So when it reacts, it can often react in radical reactions as this diradical. Now at this point you produce a peroxy radical, and that peroxy radical can now do a hydrogen abstraction on a neighboring fatty acid molecule. And so we get this hydrogen abstraction, and one electron is left here on the remaining fatty acid, and this continues. And so then this fatty acid can go back into this first step, and so on. And you end up with a lot of these hydroperoxides. So the net reaction, when we add the propagation steps, notice that here oxygen is involved, but here we produce this radical from the fatty acid, but it is consumed again, right? So these cancel each other out. Also, we produce this peroxy radical, but it is consumed in the next step. So overall, we have that a fatty acid undergoes a hydrogen abstraction, reacts with oxygen, and produces a hydroperoxide. And this hydroperoxide is again something we don't want to eat, but this regularly occurs if you just leave unsaturated fats like olive oil and stuff out in the air. We can also hydrolyze triglycerides, and so we can react with an aqueous acid or base. If we react with a base, we're going to get a so-called saponification reaction. It's going to produce the salt of a fatty acid, That's what soap is. Soap is the salt of a fatty acid. And so if we react with base, we can hydrolyze this and reverse this reaction and get the glycerol and the fatty acids. The base catalyzed hydrolysis is a nucleophilic acyl substitution. So this is a reaction that we learned about back in chapter 19, or chapter 20 rather. So the way that the saponification, which is the nucleophilic acyl substitution, works is we have an ester, and we're reacting with a base. So the base is a strong nucleophile, so this can perform a nucleophilic attack on the nucleophilic center in the carbonyl of the ester. And so again, remember, oxygen, super, this is probably the defining characteristic of many mechanisms this chapter. So if you're reviewing mechanisms, make sure you understand the conditions, acid and base, under which a nucleophilic attack occurs. It's important not only in organic chemistry but also in biological chemistry as well. So it's partially negative on the oxygen, partially positive on the carbon, and we have a strong nucleophile. So the positive carbon really is reactive towards this strong nucleophile, the hydroxide. It will attack. Now a carbon cannot have 5 bonds, so we need a resonance arrow to pair this with. Remember, here we have a pi bond between 2 atoms of differing electronegativity. So that resonance arrow goes up to the oxygen. And now this produces for us an oxygen with 3 lone pairs and 1 bond, giving it a -1 formal charge. Okay. This reaction is reversible, as we can see here. The hydroxyl could come off too. Why? Well, because this product here is itself relatively unstable, having a negative formal charge to it. And so any other alkoxy ions here will be of, similar stability. So that's why these steps are reversible. The next step as well. So the next step is propelled forward by the fact that we'll be producing, although we'll be producing an unstable alkoxy product here, this is going to leave as not a great leaving group. It's not so bad because we already had this alkoxy part here, and so it's the stabilities are relatively similar. So this will occur to a significant extent. We'll have the reforming of the quite stable carbonyl bond that recovers some stability for us, and then the loss of the leaving group. Again, this is leaving as a negative ion, not an excellent leaving group, right? It's not like a chloride or a bromide where the atom is large and it can stabilize the negative charge well. This is an oxide. Although it's an electronegative atom, it's not very large, so it doesn't stabilize that negative charge all that well. But this will be much more basic than the resulting carboxylic acid. So the remainder here is going to have a carbon double bond oxygen, which was produced when this arrow went down here. Now we have the oxygen with 2 lone pairs and 2 bonds, and we still have this OH group attached to the same carbon. So that's one right here. And this leaves us with a carboxylic acid. This carboxylic acid, of course, is much more acidic than a simple alkoxide ion, and so we'll get finally a proton transfer to produce for us an alcohol and the deprotonated carboxylic acid group. And this is why we say we get the salt of a carboxylic acid. So imagine that you added sodium hydroxide. That was your base. So sodium is an ion at the beginning, and it will continue to be an ion at the end. And so we have a salt, an ionic compound. This is the salt of a carboxylic acid. And that, the simple name for that is soap. This is soap. And if it has a sodium ion, it tends to be harder soap, like bar soap. If it has potassium ions, if you use potassium hydroxide, you tend to get softer, like liquid soaps. So, although we've seen a lot of examples where the fatty acids are all the same on a triglyceride, they don't have to be, nor are they often the same, all the same fatty acid. They'll often be a mixture of fatty acids. So when your body goes to package up the fats that you're eating, it hydrolyzes them into fatty acids if it's going to metabolize them and it metabolizes them. If you learn biochemistry later, you'll learn that it metabolizes them by chopping it from the end into 2 carbon segments and then putting that into the citric acid cycle, where it is used to in a complicated series of steps to produce ATP, or the energy molecule of your body. But notice that now your body does the other thing too. It will take fatty acids that you've eaten and it will package them up for storage as triglycerides. And when it does, it doesn't care which fatty acid it is. It will attach any fatty acid. And often these are, a number of different fatty acids here. Like in this case, we have 2 that are saturated and 1 that's unsaturated. Very, very common. Now, when we look at the different types of triglycerides here, the fatty acids found in a triglyceride, again, are often different. We'll have a mixture of these. And so the question is, on a typical triglyceride, what is the proportion of saturated fats versus unsaturated fats in the triglycerides? And if we compare, for example, beef fat and milk fat, the beef fat will be higher in saturated acids. On all the triglycerides, about 55% of those fatty acids will be saturated, and about 40% will be oleic acid, and about 3% will be linoleic acid. These are unsaturated fatty acids. And there's another 2% of other fatty acids. So you'll notice oleic acid, extremely common. And so we can see here's oleic acid. It has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 carbons in oleic acid. Here. Okay. Now, if we look at vegetable oils, the picture is very different. If we look at corn oil, the percent of saturated fatty acids, the triglycerides, is only 14%. There's about 34% oleic acid, about 48% linoleic acid. And in olive oil, it's a lot of oleic acid. We can see here, almost all oleic acid. Now, if we look at animals, different animals are going to have different percentages of fatty acids. So in humans, our fatty acids will be about 37% fatty acids. In lard, from animals, it will be about 41% from pigs. The percent of oleic acid is comparable, a little bit higher for lard, a little bit lower for human fat, and the percent of linoleic acid a little bit higher for humans. Here's a couple of other plant oils: canola oil and peanut oil. So again, it's going to depend on the plant or the animal. What is the ratio of various fatty acids? In canola oil and peanut oil, they're about similar in oleic acid. Canola oil has a bit more linoleic acid, and peanut oil has a little bit more saturated fats. And then finally, as I said, let me see where I'm at here. Yeah, as I said previously, soaps are a salt of a fatty acid. And so when we do the hydrolysis of the fatty acid with, for example, sodium hydroxide, we'll get sodium ion still as the positive ion. The negative ion will be the deprotonated carboxylic acid. And so this makes an ionic compound, which then will be solid at room temperature, as ionic compounds usually are. As I said, if we have the potassium, it'll be a kind of softer solid, like almost liquidy. And the way soap works is that soap here has a non-polar part, the hydrocarbon chain, and a polar part. So if you're trying to remove grease from your body, let's say you have some oil or grease on your body and you want to wash it off, the soap molecules, they come in a part where they have a polar head. We call this a polar head. And then they have a long non-polar chain like this, which we can use a picture like this as a cartoon. So in the oils, when you wash and you're scrubbing your hands or something, you're arranging these soap molecules such that the nonpolar parts can go and find the oils, and the nonpolar parts will stick in the oils like this, and they'll be attracted to them because they're both nonpolar. But the polar sides will be pointing away from the oils. They are not attracted to the oils. They are more attracted to water. So on the outside here will be water. And they will form what's known as a micelle. This is a micelle. And that micelle will now will now solvate the oils, allow this droplet of oil to dissolve in water, and then it can be washed away with water. Now, by the way, your body has its own molecules like this. These are called emulsifiers. And your body has its own emulsifier molecules, these large proteins that can also package oils and fats that you eat into a micelle like this that can be carried around in your bloodstream until it's dropped off in the location where the oil will be stored or used for metabolism. You can also react esters with the transesterification reaction, again from chapter 20. And so if we're reacting, instead of with a hydroxyl ion, maybe we react with like methanol as the nucleophile. And if we do this with an acidic environment, important, think about the mechanism. Since we're in an acidic environment, the first step of the mechanism will be to protonate the carbonyl. This is important because unlike hydroxide, methanol is not a great nucleophile. It's not negative. Okay, it has an oxygen atom, and the oxygen atom kind of likes its electrons, doesn't want to donate them and be a nucleophile as much as something that's negative or has a weaker grip on its electrons. And so the acid is important here to catalyze this, and then the nucleophile which is the methanol, can go and attack, ultimately be deprotonated, and we'll get this methyl ester. So essentially, the nucleophilic attack will go like after the protonation. So this is going to be protonated by the acid. We'll have a nucleophilic attack by the methanol. Then it will be protonated and will be deprotonated by water. And then we'll get the methyl ester here. And these methyl esters, methyl or ethyl esters, these can be used as biodiesel, so as fuel. The reason why we don't use the fatty acids is because, well, if we use this would be solid. Most engines cannot really cope with solids. They need their fuels to flow from a tank into the engine. And so when you create these esters, now these are liquids at room temperature, these methyl esters. And so these can flow now from your diesel tank into your engine and be burned. So again, here's the full mechanism. It's going to begin with the protonation of the carbonyl. Remember to think about why these occur, right? This is really going to help you in the end, in the final, in the ACS. When you think about why the reaction occurs, it means you don't have to memorize what's going to happen, right? I don't have this memorized per se. What I know is that there's certain things that are common. This move of protonating the carbonyl with an acid to make it a better electrophile is an extremely common move throughout this semester. And so when you see that acid and the carbonyl like this, the first thing you should be thinking is that this acid is to protonate the carbonyl, make it a better electrophile, so that it can be attacked by mediocre nucleophiles like an alcohol or like water that do not have a negative charge to them. Or don't have a sulfur atom. A sulfur atom will make something a good nucleophile because it doesn't hold on to its electrons as well as oxygen does. Oxygen is very electronegative, but we have the nucleophilic attack, and so next we're going to have the deprotonation of that. So this produces for us an unstable cation here, right? Notice here we also have this resonance arrow, which reforms forms the alcohol now. So this part here is now the alcohol. We've got that. However, now we still have this oxygen with 3 bonds and one lone pair. It's one bond to the carbon formed from this lone pair, so that's why there's only one lone pair left. And then there's still a bond to this carbon right here and to this hydrogen. So it has 3 bonds and one lone pair, giving a positive formal charge, but this can be deprotonated by the reagent or the solvent here. The methanol is probably all dissolved in methanol here, and so we remove that positive charge. Now at this time we have a hemiacetal, or not a hemiacetal, rather an ester intermediate. It's similar to a hemiacetal because it has an ether and a hydroxyl group on the same carbon, but it also has another ether group. So we're not done yet. Now we need this leaving group to leave since we're hydrolyzing this ester. So the next step is to protonate this alcohol here, which is going to turn it into a better leaving group. And this can be protonated by our protonated intermediate here. And so then now we have something that can leave as a leaving group. So the reason why this needs to be protonated is because If you have an alkoxide ion leaving, this is not a great leaving group. Now, when we saw in the base hydrolysis of esters, it did leave as a decent leaving group, but that was because the reactant that it was coming from already had a negative charge to it. So having the product have a negative charge wasn't really going uphill in energy. But if this is to leave with a negative charge on the oxygen, this is going to be very costly energetically. So we can make this a better leaving group by protonating it. And so we add a proton, making this oxygen now have 3 bonds and 1 lone pair, giving it a positive formal charge. And now it can leave as a leaving group. So we can finally reform the carbonyl here, which is going to give us back a lot of energy with that very strong carbon-oxygen double bond. And now this can leave as a neutral alcohol, which is a much better leaving group than leaving as a negative ion. Next, we have this oxygen now is making 3 bonds because it has this double bond, and 2 to carbon and 1 to hydrogen, and it has 1 lone pair. So that means it has a positive formal charge. So now this reaction is going to be taken to completion by the alcohol here deprotonating that. So we grab the proton, leave these electrons behind here, and finally we have our hydrolyzed ester. We produce an alcohol and an ester. So here this is the mechanism for the production of the methyl esters. And so that's the way biodiesel is made. So diesel can be made from like corn oil, for example, or something by this process. So that's going to be it for our first lecture. We talked about generally the different types of lipids, a little introduction. Then we went into waxes, and finally we talked about the properties and the reactions of triglycerides. When we get to the next lecture, we're going to start to talk about other lipids such as phospholipids, steroids, and so forth. So I look forward to seeing you for the next lecture. Have a good one.